Hello, everyone. This is Amit Prambar, your professor for CSC 208. Welcome back to the lecture series. And today we are going to talk about multisets and counting structures. So welcome back to Discrete Mathematics Structures. Today we are embarking on a deep dive into fascinating world of counting, formalizing how we group, arrange, and select objects under different mathematical constraints. We will also move beyond basic sets to examine structures where order doesn't matter, but repetition is allowed, the world of multisets. We will also look at advanced counting structures, binomial properties, and the beautiful pattern embedded within Pascal's triangle. This lecture is designed to transition you from intuitive counting to formal combinatorial proofs. Let's begin by looking at the core framework that governs all counting problems. So, what are the four pillars of counting? We begin our journey with the four pillars of counting. Whenever you're faced with a combinatorial problem, whether you are designing an encryption key or analyzing database schemas or calculating probability distribution, your first step must always be to ask two fundamental questions. First, does the order of selection matter? Second, is repetition of elements allowed? By answering these two questions, you instantly categorize your problem into one of the four mathematical frameworks. Over the next few slides, we will break down these categories to ensure that you have a rock-solid foundation for rest of the course. So let's talk about sets versus lists. Let's formalize distinction between ordered and unordered selections. When order matters, we are dealing with lists or sequences. For example, the list containing elements A then B is completely distinct from the list containing B then A. If repetition is allowed, a list of length k from n elements yields n raised to k possibilities. Conversely, when order doesn't matter, we are dealing with sets. In a set, the collection containing A and B is identical to the one containing B and A. If repetition is strictly forbidden, the number of ways to choose subset size k is given by the binomial coefficient n choose k. Keep these two extremes in mind as we introduce middle grounds. So the paradox of interest. Before we jump into purely formula world, let's look at the famous mathematical anecdote that highlights how deep numerical structures can run. G.H. Hardy, the prominent British mathematician, once visited his protege Hardy-Ramanujan in the hospital. Hardy mentioned that he had ridden in a rather dull taxicab number 1729. Ramanujan instantly objected, pointing out that 1729 is actually a highly interesting number, is the smallest positive integer expressible as the sum of two cubes in two different ways, 12 cubed plus 1 cube and 10 cubed plus 1 cube, 9 cubed. In combinatorics, what seems uninteresting at first glance often hides beautiful symmetric complexity under the hood. Defining n permutations. Let's formally define permutations. An n permutation is mathematically defined as a tone to one-to-one onto function, a bijection from a finite set of n elements itself. In simpler terms, it's an arrangement of all n items in a specific order. How many ways can you do that? First slot, we have n choices. Having filled that slot, we have n minus 1 choices for the second. Continuing down to single choice for the final slot. By the product rule, This gives us n factorial total arrangements. Factorial growth is incredibly steep, as we will see in the next slide. To truly appreciate the power of factorial growth, let's look at this trend visualization. At n equals 1, we have exactly one permutation. By the time we reach n equals 5, we are up to 120. We exceed 3.6 million at 10. If you were to shuffle a standard deck of 52 cards, the number of possible arrangement is 52 factorial, a number so colossally large that every time you shuffle a deck thoroughly, it's virtually certain that you are holding an arrangement of cards that has never existed before in the history of the universe. This is why optimizing permutation search algorithm is so critical in computer science. Factorials in nature. Factorials also exhibit fascinating number theoretic behaviors. Consider factorions. A factorion is positive integer that is equal to sum of the factorials of its decimal digits. There are only 4 such numbers in existence: 1, 2, 145, and 40,585. For instance, 145 is equal to 1 factorial plus 4 factorial plus 5 factorial. We also have fixed point factorials, where the number of digits in n factorial is exactly equal to n. While 1 factorial has 1 digit, higher instances like 22 factorial and 24 factorial also preserve this rare dimensional symmetry. Derangements, fixed point free. Now, what happens if we shuffle a set of elements, but we require that no element ends up back in its original position? This special class of permutation is called derangement, or a fixed point free permutation. It's denoted by subfactorial notation, exclamation mark n or d of n. A classic real-world example is a Secret Santa gift exchange, where nobody is allowed to draw their own name. Interestingly, as the number of elements n grows, the ratio of derangements to total permutation converges rapidly to 1 over e, which is approximately 36.7%. So here's a table for derangements, n equals 1 to 6. The actual numbers to see this convergence in action is shown in this table. For n equals 1, there are 0 derangements because the single element must occupy its original spot. For n is 2, we have exactly 1 derangement, simply swapping the 2 elements. By the time we reach n equals 6, there are 720 total permutations, and 265 of them are derangements. Notice how the percentage column stabilizes almost immediately around 36.8%. This tells us that if you're randomly distributing an exam back to n students, there is a roughly 36.8% chance that absolutely nobody gets their own exam back, regardless of the class size. Combinations and subsets. Now that we have mastered ordered arrangement where every element has distinct position, we transition to our next major section, combinations and subsets. Here we discard the notion of sequence and order. We no longer care about who was selected first or second. We only care about the final composition of a group. This shift in perspective simplifies some mathematical structures while introducing elegant symmetries that lie at the heart of algebraic expansions and probability theory. Combinations definition. Formally, a combination is a selection of k elements from a set of n distinct objects where order doesn't matter. The number of such selections is represented by binomial coefficient read as n choose k. To calculate this, we take the total combination of the set n factorial and divide out the unwanted orderings. Specifically, we divide by k factorial to account for the fact that the chosen elements can be rearranged in any order, and by n minus k factorial to account for the unchosen elements. This gives us our classic algebraic formula. As Matthew Macaulay eloquently noted in earlier lecture, verifying an identity by counting a set of different ways is combinatorial proof. In mathematics, algebraic manipulation is powerful, but a combinatorial proof is beautiful because it provides meaning. Instead of pushing symbols around a page, you define a concrete counting problem and you show that two different formulas both successfully solve that exact problem. Because both formulas count the same set of objects, they must be equal. We will use this exact technique to prove our next few theorems. I'll see you in the next class. Let's stop this presentation for now. Thank you.